All right, so last time we learned about field transformations. I just want to give a little bit of intuition behind what's happening in these field transformations. And I've just chosen a simple parallel plate capacitor here. This is just a space separation of charges. So imagine that you have two conducting plates. One of them is positively charged above, negatively charged below. That means that you're going to set up an electric field between the two plates. The field is going to be perpendicular to the plates. The reason for that is just, you could use Gauss's law to figure this out, but, even intuitively, if I put a test charge here, then, it's going to just get accelerated between the plates. So you get an electric field. Um, Actually, the field should be in the other direction. Sorry, if I put a positive test charge, it'll go towards the negative side. So I have the direction wrong here. Anyway, it doesn't matter. Now, let's say you're in the frame of this plate. So you see these plates at rest. And you're going to say that actually there's no magnetic field here because there's no current, right? So you're going to say there is no current. I only see an electric field and the magnetic field is zero because you need a current to generate a magnetic field. Now, suppose you have a friend who's moving with respect to this frame, where your frame, where the plates are at rest. And now your friend is going to see a current, right? Because all of these charges are going to look as if they're moving in the opposite direction. And then your friend sees a current, and then your friend says, well, the magnetic field is not zero. There is a magnetic field because I have a current. And the moment you have a current, you set up a magnetic field, just purely from Ampere's law. So what we have done with field transformations is just given like the formal relationship between the fields. Um, it's not something mysterious other than some relativistic corrections. The rest of the stuff was all there in just Ampere's law and the other Maxwell's equations. We have just formalized it mathematically, and of course included any relativistic effects which are important. So that's what's going on with the field transformations, and that's why again we said that there's no such thing as a pure electric or a magnetic field. It depends on who you ask. The only thing we can say exists is an electromagnetic field, and that's why that term is used. We say that it's an electromagnetic field for that reason. Okay. Just another thing which I want to state without proof is these are the field transformations between frames. Notice that I wrote the parallel and the perpendicular components differently. You can put all of this, just makes it more intuitive, but you can put all of that together in just one equation, right? I mean, this is equivalent to what we had before. The parallel component is still incorporated in these equations. So you can always just use these equations. So I want to state two Lorentz invariants, which, sometimes are very handy, and I'm going to state them without proof, just, to save time. One of them is E dot B. So E dot B is a Lorentz invariant. So it doesn't matter which frame you transform into, E dot B is going to be the same. Again, E square minus B square is also Lorentz invariant. So it doesn't matter which frame you measure this quantity, you're going to get the same. You're going to get the same value. And by frame, I mean inertial frames, of course, in this case. Okay, so with that, we can move on to a new topic where I find it fascinating because you'll see a little bit of connection to statistical mechanics here. But the end point of all of this is going to be for this course is going to be to derive the Lorentz transformations of specific intensity or absorption coefficient and emission coefficient, all of those quantities. And a very intuitive derivation of the Lorentz transformation there actually goes through the language of statistical mechanics. And you could do it in a different way, but I've included this here because I want to make that connection to you, because many of you have studied statistical mechanics before. So it's good to make that connection to to see the unity of phenomena. You just study these things in different courses, but in the end, there's a unifying physical phenomena there, which you're actually grasping at with all of these derivations. Now, you probably know what a phase space density is. So a phase space is kind of think of it as a 6-dimensional landscape where the 3 dimensions are spatial dimensions. So, think of a spatial cube. But you also have momentum dimensions, which are 3 momenta dimensions, right? And that 6-dimensional space is called the phase space, and a differential volume element there is called a differential, is what we'll be working with. We'll be working with a differential volume element in that 6-dimensional space. So it's going to be d cube x, d cube p, where d cube x is the volume element, d cube p is the momentum volume element, so to say. Now, what the question I want to we want to answer here is how does this transform? So how do you transform volumes in phase space? Now let's go to another frame, the primed frame. So you're going to have the volume prime is equal to the primed quantities, and I'm going to just expand them out here. And immediately you know that y and z spatial dimensions don't transform if you have a Lorentz boost along the x-axis, right? So dy prime dz prime just become dy dz. And the same thing happens to the momentum. So you can write out the 4 momentum, and only the first 2 components for a pure boost along x are going to transform. The others just remain the same. So 4 out of the 6, we're done with 4 out of the 6. So we only have to worry about 2 of them. One of them is dx prime. You again know how to transform this. This is just simple length contraction. So dx prime just becomes gamma times dx, right? So we just did this earlier when we spoke about Lorentz contraction. That leaves us with just 1 out of the 6 quantities. How do we transform this small spread in momentum? So the question we are asking is, let's imagine there are a bunch of particles. They all have almost similar x-axis momentum, but there's a very tiny infinitesimal spread in momentum. How does that tiny spread transform between 2 inertial frames? So that's the question we're asking. So we're really after this quantity here, dpx prime, okay? Now we can write out the Lorentz transformation. So dpx prime is just going to be the first element of a 4 vector. So we know how that transforms. So dpx in the unprimed frame is going to be gamma times dpx prime plus beta times d prime by c. And again, I'm going to now choose the primed frames as is been customary so far to be the frame where the small collection of particles are instantaneously at rest. Okay, so they have a tiny spread in momentum about some value, but I'm choosing a frame such that they're almost instantaneously at rest, basically. But with this tiny spread in momentum. Of course, each particle cannot be instantaneously at rest because there is a spread in momentum. But I can choose the mean value of the momentum, so to say, about which we have that spread. I can choose the frame such that they're instantaneously at rest in terms of the mean momentum of the particles. Okay, so we have this Jacobian now, which we want to calculate, dpx by dpx prime. That's just gamma times 1 plus beta by c de prime by dpx prime. So as long as I can calculate this derivative here, I can figure out what the Jacobian is, which I need to put in here to transform the volume element. So you know how to do that. So you can just start with the equation for energy. That's the relativistically correct equation for energy, and you can now differentiate that. And you basically get that dE by dpx is just c squared times px by e. Okay, that's the derivative we are after here. So you just put primed quantities here, and then the value of the derivative. Now the fun thing is, once I go to a frame where the particles are instantaneously at rest about that mean value px, of course, right? There is a small spread, but we're trying to find this derivative here. When the particles are instantaneously at rest, your px is going to be px prime is 0 in that frame because the particles are instantaneously at rest. So they don't have any momentum. You can kind of also see it here that the spread of energy is going to be almost 0 in this frame because the particles are instantaneously at rest. But again, they have a small spread in momentum. So you actually, they actually also have a small spread in energy. So you actually have to go through the math here to make sure you get the right answer. So this becomes 0 in that special frame. Okay, only in that special frame, this becomes 0. So you basically get dpx equal to gamma times dpx prime. You put everything together, the 2 gammas cancel off, and then you basically get, the 2 are equal. The phase space volumes are equal between the 2 frames. And so what ends up happening in this case is the phase space volume is just equal, even though you go through a Lorentz transformation. So that must actually just be a Lorentz scalar. So phase space volume element is Lorentz invariant. So consequently, the phase space density is a Lorentz invariant. And the reason for that is the phase space density is just the number of particles divided by a volume element. and the number of particles is a countable object, so that's always Lorentz invariant, and the volume element is Lorentz invariant. So which means the ratio is also Lorentz invariant. And so we have this nice result, which is that phase space density is always a Lorentz invariant. Okay, so that's kind of a quantity which is important, and that's how things become important. This quantity also becomes important in thermodynamics for other reasons, but it's also important when you're dealing with relativistic mechanics, because this quantity is Lorentz invariant. So you can always go, transform this quantity very easily. It's the value is the same in different frames. Now, how are we going to use it? So the way we're going to use it now is we're going to relate the phase space density with intensity, which we studied in week 1, right? So I'm talking of specific intensity here, which is ergs per second per hertz per square centimeter per steradian, okay? And I'm going to try to find a relationship between this and the phase space density of photons. So now we're talking of phase space density of photons, okay? By the way, this is true for any particle. We're just going to apply it to photons now. Now, the easiest quantity we can kind of bring in the phase space density through is this energy density, which we also encountered in the first week. That's because it just becomes easy to relate densities once you have the energy density in terms of some kind of a flux which is per square centimeter. So we actually derived this in week 1, where the energy density, now measured in ergs per cubic centimeter per hertz per steradian, is equal to just the specific intensity divided by the speed of light. Okay, so we just derived this in week 1. You can go back to your notes from that week. Now, let's actually try to write out this energy density in terms of the phase space volume element. So let's say dN by dV is basically the density of photons in this 6-dimensional phase space. So this is just the number of photons per unit volume element. And so if I multiply that by the volume element, which is d cube x d cube p, I get the total number of photons, right? And so those photons have energy nu. So if I multiply that by h nu, then I'm going to get the total energy in this element, in this phase space elemental volume. So the right hand side has units of ergs, right? So now I take this quantity u I have, I multiply that by the differential solid angle, multiply that by the frequency spread and the volume element. Okay, so now u multiplied by these 3 again has units of ergs. So we're just trying to find what is the total amount of energy in a solid angle element d omega, in a frequency range d nu, in a volume element d cube p. Okay, so that's ergs, the total amount of energy. And we did the same, but now just counting photon energies on the right hand axis here. Okay, so d cube x immediately cancels off. That's easy on both sides. So that on the left, it just leaves us with d omega d nu. Okay, we'll leave that as is for now. And of course, u is I nu by c. So I've just put it in here. So I've brought in the specific intensity here. And now on the right, I have this d cube p. Okay, so I can now write d cube p as p squared dp d omega. So this is just the volume element, but now I've written it in spherical coordinates. So this was in Cartesian coordinates, and in spherical coordinates, the volume element is r squared dr d omega, right? So r being the radius vector in spherical coordinates. So I've just written, this is just the differential volume element in spherical coordinates. Okay, so now we get rid of d omega, right? The d omega is gone. Okay, so we get here where you have I nu by c d nu, and then now d omega is gone. So that's what we have on the right hand side axis. Now we can write for photons, P is equal to h nu by c, because momentum is equal to energy divided by c for photons. So P square can be written in terms of frequency alone, and dP can also be written in terms of d nu, the frequency alone. So now we get rid of d nu on both sides, right? And then you put all of that together, you can pause and do the algebra. You arrive at this equation where you have I nu by c equal to the phase space density of photons nu cube. That nu cube came from p squared dp, where p is h nu by c, and some fundamental constants. H and c are Planck's constant and the speed of light. These are constants. Now dN by d nu is a Lorentz invariant. That means that if I bring the nu cube to this side, to this end, I get I nu by nu cube. The right hand side is a Lorentz invariant, so this has to be Lorentz invariant. Okay, so now you immediately know how I nu is going to transform, because you know how nu transforms, right? So you go back to your formula for relativistic Doppler shift. This is how nu transforms. And now you know that I nu by nu cube has to be Lorentz invariant. So you can immediately figure out how I nu is going to transform. So you know how specific intensity transforms now. Okay, so what about absorption and emission coefficient? So let's start with absorption coefficient. So let's assume that you have some medium here doing the absorption, and you're viewing that ray going through the medium getting absorbed in two frames, K frame and K prime frame. And so that ray, again, because of aberration, is going to make different angles, right, in the two frames. And let's say there's a velocity v between the two frames, okay? So one thing we can start with here again is that the optical depth must be Lorentz invariant. And the reason for that is the optical depth just determines what fraction of photons are absorbed, right? It's again a countable thing. If I have 100 photons, you know, how many out of them get absorbed? That's a countable thing. And so that must be a Lorentz invariant. So we know that tau, the optical depth, is Lorentz invariant. So if you actually write down explicitly what tau is just going to be, you know, some thickness of the medium. I mean, this thickness, you know, can be a differential element. It doesn't matter. I've just taken L, but you can actually imagine an extended medium and just write out a differential element and write this whole thing as an integral. It doesn't make a difference. You'll get the same answer. So L times the absorption coefficient alpha divided by sine theta, right? That's the optical depth. Because L sine theta is basically the distance which the ray is traveling in the medium. And so, you know, you can write this in any frame, okay? This, you know, I can put primes here and then everything should still be the same. Anyhow, so this has to be Lorentz invariant, which means that alpha nu by sine theta is Lorentz invariant. Why is that so? Because L, I've just chosen L to be perpendicular to the velocity direction, right? So I've basically put all the complexity in that angle theta there by just choosing my variable as I've just, you know, if you put it as an integral, you know, you're just casting this integral as a function of the y-axis here. Okay, you can always do that for an extended medium. You can actually define the integral along the y-axis. I mean, of course, you would have to do an integral along the ray, but you know, I can cast it as an integral along the y-axis and put sine theta in the denominator. It's the same thing. Okay, so alpha nu by sine theta has to be Lorentz invariant, and then you're done, right? Because you know how sine theta transforms. Sine theta just transforms, you know, from the aberration of light formula. You can go back to your transformation of velocities from which we derive the aberration of light, and you know how sine theta transforms. So you're basically done here. If you know how sine theta transforms, you know how alpha transforms because the ratio is Lorentz invariant. You can play a little trick here. Instead of going through the aberration formula, you can just multiply and divide by nu on both sides, on the numerator and denominator. So you get alpha nu times nu, and in the denominator you get nu sine theta. So what is nu sine theta here? If I put h here, the Planck's constant, that is just the y component of the photon momentum, right? So nu times sine theta. So the photon momentum is going in this direction. Times sine theta is going to be the y component of that momentum. And of course, the relative velocity, the boost, is along the x-axis. So the y component of the momentum cannot change. So nu sine theta has to be a Lorentz invariant because that is just some fundamental constant times the y component of the photon momentum. That means that alpha nu times nu also has to be Lorentz invariant because the ratio is Lorentz invariant. And you know how nu transforms. So now you know how alpha transforms. Okay, how would you do emission coefficient? Well, you know, that's very simple because you have Kirchhoff's law, right? You know how alpha transforms. This is basically Planck's function, but this is just specific intensity, right? Planck's function is just a special case of specific intensity. And we know how that transforms. We just did that. So B nu by nu cube is Lorentz invariant. Alpha nu times nu is Lorentz invariant. So, you know, you write all of those things out and then you again argue in the same way. And then you end up saying that the emission coefficient divided by nu square becomes Lorentz invariant. Okay, so that's how you would transform all of these quantities. And so I hope you enjoyed going back to some ideas in statistical mechanics, but also having a call back to week 1 where we did radiative transfer. And you know, now we come a whole circle with our discussion of, you know, relativistic covariance of electromagnetic phenomena. So you know how to do the different mechanical things like momentum, distance, time dilation. You know how to transform wave vectors. You know how to transform velocities, the aberration of light. So you know how to do all the mechanical stuff. You also know how to transform fields. Um, and now you also know how to transform the more, how do you say, the integrated quantities like, energy density or specific intensity, absorption, emission coefficient. So now you know how to Lorentz transform almost all the quantities we have dealt with so far in the course.